Hello, viewers, and welcome back to the Sleepy Narrator. I'm so glad you're here. Whether you're lying down in bed with the lights dimmed low, slowly sinking into your pillow, or curled up on the couch letting your mind drift like a leaf upon still water, this space is made for you. Tonight, we begin something quietly remarkable. We'll drift together into the world of time, not only what it is, but how it bends, stretches, and slips softly beneath your feet without you even noticing. The story of time dilation isn't simply science, it's poetry hidden within the laws of the universe. It's about the shape of waiting, the weight of speed, and how two hearts can beat apart within the same moment. I should gently warn you. This tale may soothe you so deeply you drift away before the end. But if it keeps your thoughts glowing a little too long, even wakefulness can be restful when it's filled with wonder. If this moment brings you peace, I'd be grateful if you left a quiet like, and maybe subscribed for more dreamy explorations of science. And if you're comfortable, share where you're listening from and the time there. It's always a joy to see our map of rest stretching across the world. This story is meant for gentle learning and relaxation only. It's not a substitute for medical advice or professional care, just a safe harbor to fall asleep with curiosity close at hand. Your body feels still tonight. Your breathing has slowed, the room is quiet, and the clock on the wall ticks in rhythm with your heartbeat. It all seems steady, absolute. But what if I told you that clock is lying? Not intentionally, of course. It's doing its best, but time isn't as simple as the rhythm it pretends to keep. Time is more like a soft flowing current. Your body, your thoughts, your memories, they are tiny boats adrift on it. And sometimes, without ever noticing, your little boat floats faster or slower than someone else's. This is time dilation. It sounds technical, but let's feel it instead. Picture two birds flying side by side. One soars higher, brushing the edge of the sky where gravity loosens its pull. The other glides low where the earth holds tight. Their wings beat in sync. Yet when they meet again, they are not quite the same. One has aged a little less. A few heartbeats spared, a small ripple in time's quiet stream. Time bends when things move quickly. It bends when they're near something massive. This isn't fantasy, it's Einstein's gentle, revolutionary truth. Time is stitched into space, a fabric called spacetime, and like any fabric it can wrinkle and stretch. You felt time shift, haven't you? In joy, hours slip away like mist. In waiting, for news, for healing, for someone, each second expands, heavy and slow. That feeling isn't only in your mind. It's a faint echo of what the universe does on larger scales. Imagine floating through space beside the International Space Station. From Earth, it seems you are circling quickly. But up there, time passes just a little slower for you than for someone on the ground. Not by much, mere microseconds, but over enough time it adds up. Astronauts return slightly younger than if they'd stayed here. They don't notice, not really. There's no sudden shift, no hiss or glow of a time machine, just a quiet gift from speed and gravity, a moment folded inside another. That's the secret. Time dilation doesn't feel like anything. It doesn't sting or shimmer. It hums beneath your senses, unnoticed, like the faint vibration of a deep cello note long after it's been played. So tonight, as you rest, you might wonder, does time flow evenly in this room? Is your head aging at a slightly different pace than your feet, pulled ever so gently by gravity? The answer, curiously, is yes. The difference is unimaginably small, a fraction of a second across your whole life, but it is real. By lying here on Earth, you are living proof that time is elastic. Let your thoughts stretch with it. Imagine a mountain, tall and still. A clock at its base ticks faster than one perched at its peak. Why? Because the mountain's summit is farther from Earth's center, where time flows a little more freely. That's how delicate the universe is, how precise, how quietly strange. You're not just a witness to time, you carry it. Every cell in your body keeps a rhythm. Your memories are woven through time's gentle threads. And as the cosmos spins, planets whirl, and galaxies race away, you move with them, your own little timeline swaying among giants. This is why GPS satellites need special clocks. They orbit Earth far above, moving swiftly and light in gravity's grasp. If their clocks ticked like ours, they would fall out of sync. So they're adjusted constantly to account for time's stretching and slowing. The maps you follow, the phone you carry, the navigation you trust, they all depend on a universe where time is never exactly the same in two places. So tonight, as you fall towards sleep, imagine time not as something rigid and ticking, but as something soft and flowing, a river with eddies and whirlpools with silent depths, and you floating gently upon it always. In this next step of our quiet journey, we move deeper into the delicate folds of time, exploring how speed reshapes it in ways that feel impossible, yet are entirely real. Time's gentle bending isn't limited to faint differences in ticking clocks or tiny shifts in seconds. At extreme velocities, its effect becomes profound, altering the very rhythm of life. Imagine stepping into a sleek, silent vessel, resting just beyond the edge of Earth's atmosphere. Around you there is no breeze, no sound, only the soft hum of machinery and the steady rhythm of your breath inside your helmet. With a gradual surge of power, the craft begins to accelerate, faster and faster still. Below, Earth's curve shrinks, the blue deepens, clouds coil into slow spirals. Stars that once seemed motionless begin to stretch ever so slightly, their light drawn thin across space. And then something remarkable occurs. Time slows, not for you because you feel no change, but for those watching from Earth. To them, your seconds stretch a little longer, your movements appear more measured, as though the universe itself has adjusted the tempo of your existence. This is the quiet grace of high velocity. The nearer you approach the speed of light, the more time tilts in your favor, allowing less of it to pass for you than for those you left behind. You've done nothing unnatural, only moved quickly through space, and the universe simply allows your clock to run more slowly. This is no science fiction. It is the very essence of Einstein's theory of relativity, confirmed by countless experiments. At great speeds, time genuinely moves at a different pace for you, not as an illusion but as a measurable fact. Picture two identical clocks, one left on Earth, the other traveling beside you at near light speed. When brought together again, the traveling clock will have counted fewer ticks. You will be younger, your skin, your cells, your very thoughts, than those who remained at home. Even the fastest aircraft and orbiting satellites experience this effect, though so slightly that only the precision of atomic clocks can measure it. But imagine the scale of a voyage to a distant star at near light speed. You might leave for what feels like a handful of years, only to return to find decades have passed on Earth. Children grown, cities transformed, histories written without you. For you, only a short time has passed. For the world, your absence stretched across an age. Time, something we believe to be universal, is in truth personal. It depends on the path you take through space and the speed at which you travel. You are not escaping it. You are simply moving through it differently. It's like swimming in a thick, slow-moving current instead of clear water. The faster you push forward, the more the flow resists, and the greater the shift in your own passage through time. At rest, all feels stable. But as speed rises toward light's velocity, clocks start to disagree, and with them everything else. Your heartbeat, your breath, your thoughts, each is bound to time's flow. Imagine traveling to Proxima Centauri, our closest stellar neighbor, over 4 light-years away. At near-light speed, your journey might seem to last only days. Yet back on Earth, years would roll by. Seasons would turn, lives would change, and when you returned, you would carry the past into a world that had long moved beyond it. It's as if you had been sealed in a bottle and set adrift on time's river, only to wash ashore in a future that waited patiently for your arrival. And remember, it isn't only speed that can reshape time. Gravity can do the same. But here, at the edge of velocity, one truth remains. No object with mass can reach the speed of light. The closer you come, the more energy is needed and the more your seconds stretch. For light itself, weightless and unbound, time does not pass at all. A photon, leaving a star and striking your eye experiences no before and after, only a single, unbroken moment. You, bound by mass, travel through time like a swimmer through an endless current. And when you return from the heights of speed, you bring with you the subtle proof of that passage. Even now, in stillness, you are not at rest. The earth turns beneath you, it circles the sun races through the galaxy. You are moving through spacetime at incredible speeds, shaping time in ways too small to feel, but too real to deny. Perhaps that is why some nights feel different, why dreams sometimes seem longer than the hours allow. Deep within, your body may already know what your mind is only now considering. Time is never truly still. Speed is not the only sculptor of time. Gravity also bends it, shaping the very rhythm of existence in ways we can measure, though we cannot feel them. Think of gravity as more than a pull. It is a curve in the fabric of spacetime. Anything with mass presses into that fabric, creating a dip, a slope, a valley that everything else must follow. The stronger the mass, the deeper the curve. And here lies the subtle truth. The deeper you are in that gravitational well, the more time slows for you compared to someone farther away from it. This isn't imagination. It's an effect confirmed by careful measurement, even here on Earth. Place two identical atomic clocks, one at the base of a tall building, another at its top, and the lower clock will tick more slowly. The difference is minuscule, but it is real. It happens because the clock lower down is sitting deeper in Earth's gravitational pull, and time itself is flowing a fraction more slowly there. Now, stretch this idea outward into the cosmos. Picture a spacecraft hovering just above the surface of a neutron star, an object so dense that a teaspoon of its matter would outweigh mountains. Its gravity would be so intense that time there would crawl compared to the rhythm in deep space. Minutes for the crew could be years for observers far away. And then, beyond even neutron stars, there are black holes, the ultimate wells in spacetime. Their gravity is so fierce that nothing, not even light, can escape from within a certain boundary called the event horizon. As you draw near that invisible edge, something strange happens. To you, time seems normal. You speak, you breathe, your heart beats in its usual pattern. But to anyone watching from far away, your actions appear to slow and slow until they nearly freeze. From their perspective, you never quite cross the event horizon. You fade, your light stretches redder and redder, your image dissolves into darkness. But for you, if you could survive the journey, time would carry you onward beyond that point into a place the outside universe could never see. This is not fantasy. It is the nature of spacetime under the weight of extreme gravity. The closer you are to a massive object, the more your time diverges from the time of someone farther away. And this means something remarkable. By simply changing your position in a gravitational field, you can change the pace of your life compared to others. You could, in theory, leap forward into the future, just by waiting near something incredibly massive. It's the same principle that makes GPS satellites require constant adjustment. Orbiting far above Earth's surface, they feel less gravity than we do here below. Their clocks tick faster because time flows a little more freely for them. If engineers ignored this, your navigation would wander wildly off course within hours. Einstein's general theory of relativity doesn't just predict these effects, it demands them. Space and time are woven into a single fabric, and mass tells that fabric how to curve. That curve, in turn, tells matter and light how to move, and it also tells time how to flow. For most of us, living in everyday conditions, these differences are so tiny we never notice them. But they are always there, quietly shaping the universe's rhythm. Every mountain peak and valley floor, every orbiting satellite, every drifting comet, each exists in its own version of time. Imagine a clock fixed to the surface of Jupiter, a world more massive than ours. Time there would run slower than here on Earth, pulled back by the planet's heavier gravity. And if we traveled to that clock, we would feel no difference. Yet returning home, we would discover that Earth had aged a little more while we were away. Gravity and motion together form the keys to time travel, not the wild, fictional kind with glowing portals and sudden leaps, but the real, measured journey that physics quietly allows. They cannot take you into the past, but they can carry you into the future, simply by choosing the right path through spacetime. This is why scientists often speak of astronauts as time travelers, even if their leaps are only by microseconds. The principle is the same whether you gain a fraction of a second or decades. Time is personal, elastic, and deeply tied to where you are and how you move. It also means that, in a way, the universe is full of countless timelines, all overlapping but never quite identical. Your life, my life, the life of someone on a distant planet, all run at slightly different speeds, connected by the same cosmic fabric but not bound to a single universal clock. And somewhere, perhaps near the edge of a black hole, time is stretching so far apart from hours that what we call a second there might be centuries here. The thought is both humbling and oddly comforting. It reminds us that time is not an enemy to outrun or a wall to break through. It is a landscape, and we are travelers moving through it, each on our own winding path. When we talk about time travel, most people imagine jumping backwards, slipping into the past, stepping into moments long gone, rewriting history or watching it unfold with fresh eyes. But physics tells a different story. Moving into the past, at least as we currently understand the laws of the universe, appears impossible. There's no known way to cross that line without breaking the very structure of causality, where causes come before effects and events follow a logical order. If time could loop back on itself freely, paradoxes would arise. A traveler might alter events that prevent them from making the journey in the first place, creating contradictions that the universe's rules do not seem willing to allow. This is why relativity, while opening doors into the future, keeps the past firmly closed. It allows you to skip ahead, to live less time than those around you, but not to reverse the sequence of cause and effect. That doesn't stop our minds from wandering there. The idea of revisiting the past is alluring, perhaps to undo a mistake, to relive a joy, or simply to stand again in the light of a day we've lost. Yet even without backward travel, there is a kind of time journey we all make without noticing. Memory allows us to step for a moment into the echo of what has been. When you close your eyes and recall the laughter of a loved one or the scent of rain on a summer street, you're walking a quiet path through your own timeline. Physics can't send us there, but the mind can. In the world of science, however, moving forward in time is not only possible, it's already been done, in small ways, every day. Astronauts circling Earth on the International Space Station return fractionally younger than their twins on the ground. Their speed and position above our planet shift the pace of their lives, nudging them slightly ahead into the future. This is the essence of time dilation at work. Your personal clock can tick at a different speed from someone else's. The effect can be magnified by velocity or by resting deep within a strong gravitational field. Theoretically, if you could travel close enough to the speed of light, you could make enormous leaps forward in time. For you, only months or years might pass, while centuries race by for those who stayed behind. Stories often call this the twin paradox, but in reality, it's no paradox at all. It's simply the outcome of two paths through spacetime that are not the same. One twin remains on Earth's gentle curve, the other bends their route through high speeds, and when they meet again, their clocks no longer agree. And so, time travel into the future isn't a matter of stepping into a machine and spinning dials. It's a matter of choosing the right journey. Long, high-speed voyages, or extended stays near massive objects, are the tools the universe offers. It's important to remember, though, that for the traveler, time feels perfectly normal. They breathe, they eat, they think, all at the usual pace. It is only when comparing with those left behind that the difference reveals itself. This is perhaps the most poetic truth of all. You can be a time traveler without even feeling it. You can move ahead into a future someone else cannot yet reach. And to you, It feels no different than living a single, continuous moment. And if you look closely, you'll see that we're all doing this already. Each of us is carried forward second by second, never pausing, always in motion. The only difference between the ordinary passage of time and the extraordinary is the size of the leap. When you think of it that way, time travel isn't something far off or unreachable. It's simply the nature of existence. Every breath, every blink, every thought is part of your voyage, through days, through years, through the entire lifespan of the universe. Throughout history, people have been fascinated by the idea of traveling through time, not just moving forward into the unknown future, but also stepping backward into the past. Ancient myths and modern fiction alike are filled with stories of characters who leap across the timeline, visiting ages long gone or worlds yet to come. But while physics offers real, measurable ways to move into the future, stepping into the past presents a much deeper challenge. Our current understanding of the universe's laws simply does not allow for easy reversals of time's arrow. Time's arrow is the idea that events move in a single direction, from cause to effect, from past to present, and on into the future. The laws of thermodynamics, especially the concept of entropy, give this arrow its meaning. Entropy measures disorder, and the natural tendency of the universe is for disorder to increase. A dropped glass shatters, heat spreads into cold air, and memories form in the present about the past, not the other way around. Reversing this process would not just be difficult, it would require breaking the fundamental rules that hold the universe together. And if those rules were broken, paradoxes could emerge. One famous example is the grandfather paradox. Imagine you traveled into the past and prevented your grandfather from meeting your grandmother. This would mean you could never be born, and therefore could never have traveled into the past to cause the change in the first place. The sequence collapses into contradiction. For reasons like this, many physicists believe that traveling backward through time, at least in a way that lets you change events, may be impossible. Some theories propose that the past is fixed, and even if you could somehow visit it, you would not be able to alter anything. Others suggest that if backward travel is possible, it might lead to branching timelines, where each change creates a new reality separate from the one you left. But these remain speculative ideas, with no evidence yet to support them. The known, proven effects of relativity keep our travel pointed toward the future, not the past. Yet the mind has its own form of time travel. Memory allows us to step for a moment into days long gone. When you recall the scent of fresh rain, the feeling of a hand in yours, or the sound of laughter in a childhood room, you are briefly transported, not physically but emotionally, into another point in your life. Dreams can do this too, taking you to moments that feel vivid and real, even if they are entirely imagined. Your mind becomes the vessel, carrying you through your personal timeline. In the physical world, though, the most direct and reliable form of time travel remains what Einstein's theories describe: moving forward at a pace different from those around you. This is achieved through high speeds or strong gravity, both of which change the rate at which time flows for you compared to others. Imagine boarding a spacecraft capable of traveling at 99% of the speed of light. From your perspective inside, time passes normally. You eat, sleep, and think at your usual rhythm. But for people on Earth, your journey takes far longer. If you spend 5 years on your ship, decades or even centuries might pass back home. This is not science fiction. It is a natural outcome of how spacetime behaves. The faster you move relative to someone else, the more your clock slows compared to theirs. This is the principle behind the famous twin scenario in relativity. One twin stays on Earth, while the other embarks on a high-speed journey through space. When the traveling twin returns, they are physically younger than their sibling. They have quite literally stepped into the other's future. We already see smaller versions of this in real life. Astronauts aboard the International Space Station orbit Earth at high speeds and at an altitude where gravity's pull is slightly weaker. Because of this, they experience time passing a little slower than people on the ground. Over the course of a 6-month mission, the difference is tiny, mere fractions of a second, but it is measurable. In more extreme conditions, such as near a black hole, the difference could be massive. Time near the event horizon of a black hole slows so dramatically compared to distant observers that minutes for someone close to it could equal years for someone far away. This means, in theory, that a person could use the gravitational field of a massive object as a kind of time machine, by waiting close to it, then returning to a place where time has passed much faster. Of course, in practice, getting near a black hole is impossible without being torn apart by its tidal forces. Still, the concept stands as one of the most striking demonstrations of how gravity and motion can bend time. It also shows why the concept of universal time doesn't really exist. There is no single, shared clock that ticks the same for everyone in the universe. Time is personal. It depends on your location, your motion, and the gravitational fields you experience. This also means that if intelligent civilizations exist far across the cosmos, they may live in timescales very different from ours. Their seconds could be longer or shorter than ours, depending on the conditions of their home worlds. Communication with them would involve more than just learning a language. It would mean adjusting to an entirely different rhythm of existence. When you think about it, this is extraordinary. We live in a universe where each of us carries our own private timeline, shaped by the path we take through space and the gravity we feel. Even here on Earth, time is not perfectly uniform. Your head ages slightly faster than your feet. Your watch ticks at a different pace in the mountains than it does at sea level. Yet for all these differences, we share enough of the same rhythm to live, work, and dream together. So while we may never walk into the past the way stories imagine, we are all already moving into the future at our own pace. And if we choose the right path, whether through speed, gravity, or both, we could leap ahead into that future in a way that feels almost magical, yet is entirely real. And perhaps that is the most fascinating thing about time travel. It is not about breaking the rules of the universe, but about understanding and using them. The possibility of traveling into the future through speed and gravity is more than just a thought experiment. It's something we can plan, test, and calculate with astonishing precision. Relativity gives us the equations, and the universe itself provides the settings where they can be applied. But in exploring these ideas, scientists often stumble upon concepts so strange they almost feel like fiction, yet they're rooted in the mathematics of spacetime. One of these concepts is the wormhole. In the simplest terms, a wormhole is a tunnel through spacetime that connects two points that might be separated by great distances. Imagine folding a sheet of paper so two points touch, then poking a hole between them. That hole is the shortcut. In theory, wormholes could connect not just two locations in space, but two moments in time. If one end of the wormhole experienced time differently from the other, say, by being placed near a massive object or sent on a high-speed journey, then stepping through could move you into the past or future relative to where you started. It sounds like pure fantasy, but the math of general relativity doesn't forbid it. However, the obstacles are enormous. Wormholes, if they exist, would be unstable, collapsing before anything could pass through, unless held open by a form of matter with negative energy density, something we've never observed in large amounts. Still, the idea captures our imagination because it hints at possibilities beyond the steady, forward march of time we experience here on Earth. Even without wormholes, spacetime itself can curve and twist in unusual ways. The universe is not a rigid stage, it's a flexible fabric. Mass bends it, motion warps it, and under extreme conditions it can form loops. Some solutions to Einstein's equations suggest that if spacetime were twisted in just the right way, it could, in theory, create closed time-like curves, paths that loop back to the same point in time. Physicists debate whether such curves could actually exist in reality. Many suspect that unknown laws of quantum gravity would forbid them, preventing the possibility of traveling into one's own past. But until we understand the universe on its smallest scales, the door remains slightly open. In the meantime, we focus on what's proven, the way speed and gravity can shift the pace of time. This is the kind of time travel we can demonstrate right now with technology we already have. Atomic clocks, our most precise timekeepers, have been flown on airplanes, launched into orbit and placed on mountaintops. Every time, the results match Einstein's predictions. The clocks in motion or in weaker gravity run faster or slower than those at rest in stronger gravity. We can even see time dilation at work in the subatomic world. Particles called muons are created when cosmic rays strike Earth's atmosphere. These muons decay quickly, usually in millionths of a second. But those moving close to the speed of light live longer than stationary muons, simply because their internal clocks are running slower. Without time dilation, they wouldn't survive long enough to reach detectors on the ground. This is one of the most beautiful things about physics. The same rules that apply to the tiniest particles also govern planets, stars, and galaxies. Time dilation is not a quirk, it's a fundamental part of reality. And this reality means that if you want to step into the far future, you don't need magic. You just need to move quickly enough or wait in the right place. But here's the paradox of possibility. While physics allows it, engineering does not. At least, not yet. Reaching speeds close enough to lights to create significant leaps in time would require vast amounts of energy. The faster you go, the more energy you need, and the increase is exponential. At 99% of light speed, your clock might slow enough to let you skip decades in a few years. But at 99.999%, you'd need energy almost beyond imagining. Gravity offers another route, but to experience dramatic time dilation, you'd need to be near something incredibly massive, like a black hole. And while the math is elegant, the reality is harsh. The same forces that slow your time could also tear you apart. Still, knowing that the rules allow it changes the way we see the universe. Somewhere out there, perhaps near the rim of a supermassive black hole, time is already flowing differently. If a civilization could survive there, their seconds might be our years. And to them, our history would race past in the blink of an eye. This thought stretches our sense of scale. It means the universe is not a single clock, ticking evenly for all, but a vast network of personal timelines, each shaped by its own journey through spacetime. We are, all of us, already traveling into the future. We do it slowly together, sharing days and nights. But the physics of relativity reminds us that the rate of this travel can change. Perhaps, one day, humanity will build ships capable of such journeys, vessels that sail not just through space, but through time itself. They might leave Earth for a voyage lasting only a few years on board, yet return to a planet centuries older. For the travelers, it would be a leap forward into a world transformed. Languages evolved, cultures shifted, continents changed by time's hand. It's a strange thought, both thrilling and bittersweet, because while you can move forward and see what's to come, you cannot move backward to reclaim what was left behind. And maybe that's why time travel captivates us so deeply. Not because we want to see the future, but because we long for the past. We feel the weight of time because it moves in one direction, and each step forward carries us farther from the moments we cannot return to. Yet within that truth lies a kind of beauty. If we could live forever in the past, we might never move toward the unknown. The forward flow of time pushes us to grow, to explore, to create. And as you listen now, you are traveling, not in some far-off science fiction sense, but in the most real way possible. Every second is a step, every heartbeat a mile marker, carrying you onward through the story of the universe. The difference between ordinary life and extraordinary time travel is just the size of the leap. And the physics that governs that leap is already here, waiting for us to use it. When you imagine time travel into the future, you might picture a sudden jump. One moment you're here, and the next you've arrived years or centuries ahead. But in reality, this leap would feel nothing like that. For the traveler, there would be no sense of skipping. Every second would seem normal, every heartbeat steady. Meals would be eaten, conversations held, sleep would come and go in its usual rhythm. The only difference would be the world you step into when the journey ends. That's the quiet beauty of relativity. Time doesn't vanish, it stretches. And that stretching means you can live fewer moments than those who remain behind, while still experiencing life as you always have. Imagine a ship leaving Earth at extraordinary speed. From your perspective inside, the voyage lasts 2 years. You mark the seasons, celebrate birthdays, and watch the stars slide by your window. But when you return, decades have passed on Earth. People you knew may be older or gone, cities altered, landscapes changed. You have not simply traveled through space, moved through time. This is why scientists call astronauts time travelers, even if their gains are measured in microseconds. The principle is the same, whether the leap is tiny or vast. But the mind resists this idea because our everyday experience tells us time is steady. We expect clocks to agree, no matter where they are. It feels unnatural to think that two people can live side by side and yet age at different rates. And yet, we know it happens. High-speed particles last longer than they should. GPS satellites need constant adjustments because their clocks tick faster than those on Earth's surface. These are not theories anymore, they are measurements. It's in these measurements that the possibility of greater time travel emerges. If you can amplify the conditions, push the speed higher or the gravity stronger, you can magnify the effect. Think about a massive star collapsing into a black hole. Near its surface, gravity is so intense that time slows dramatically. If you could safely orbit close to it for a short while, then return to a calmer region of space, you would find that the outside world had aged far more than you had. Of course, safely is the challenge. Black holes are not gentle companions. Their tidal forces could tear matter apart and the radiation near them could be lethal. But the physics still stands. The closer you are to such a massive object, the more you step out of sync with the wider universe. There's something haunting about this. A traveler could set out on a journey and return to find centuries have passed. The civilization they left might no longer exist, its languages forgotten, its cities crumbled. To them, the journey was brief. To the world, it was an absence that lasted lifetimes. Science fiction often plays with this idea. Explorers setting out into deep space and returning to find their homeworld changed beyond recognition. But the truth is, such a scenario is entirely possible, given the right conditions. And it's not just black holes that can do this. Any massive body causes time to slow in its vicinity. The effect is small on Earth but grows with size and density. On a supermassive planet, or in the depths of a neutron star's gravity well, the difference could be immense. This raises an intriguing question. Could there be places in the universe where life evolves under such conditions, experiencing time so slowly compared to us that we would never notice their existence? Their civilizations might live through what they feel are thousands of years, while to us, those same centuries might pass in moments. If that's true, it means the cosmos could hold countless timelines flowing at different speeds, layered and overlapping like currents in an unseen ocean. In this ocean, every traveler sails their own course. You are on one now, bound to Earth's gentle pace, moving steadily into the future. If you change your speed or location, you can change that pace. Relativity makes this not just a poetic idea, but a measurable one. It means time is personal, an intimate part of your journey, shaped by your path through the universe. And perhaps that's why the concept of time travel feels so human. It's not only about reaching the future, it's about what we leave behind. Every leap forward carries the weight of separation, the people, places, and moments that cannot follow. This is the bittersweet truth of forward travel. You can see the world that will be, but you can never step backward into the one that was. And maybe that's why we're drawn to it. The future is unknown, and in it lies the promise of discovery, of seeing things no one else has seen. But it also asks us to accept that what we leave behind will be changed, perhaps beyond recognition. It's the same feeling that comes with every step forward in life. Moving into the future is what we all do every moment, whether we want to or not. Time travel in its grandest form is simply that motion writ large. And so, as you picture the vastness of space and the strange ways time bends within it, remember this. You are already a traveler. You are already moving toward a future no one else has lived. The only question is how far and how fast you want to go. When we speak about the physics of time travel, we often focus on the science that works, the principles we've proven, the effects we've measured. Yet equally fascinating is the boundary between what's possible and what might forever remain unreachable. For instance, many wonder, if the universe allows time to slow down for some, could it ever allow time to reverse? Could we, under certain circumstances, step backward into what has already happened? The laws of relativity suggest that spacetime can, in theory, be curved in complex ways. Certain mathematical solutions to Einstein's equations, like those involving rotating universes or exotic matter, can produce closed time-like curves. These loops would allow a traveler to return to an earlier point in their own history. But while the math works on paper, the real universe seems far less accommodating. Such curves would require conditions and materials that we have no evidence of, and perhaps that cannot exist at all. Many physicists believe there's an underlying principle, not yet fully understood, that quietly prevents the formation of these loops. One reason is the problem of causality. If you could travel into the past and change something, no matter how small, it could ripple forward and alter the present. The grandfather paradox is the most famous example, but there are countless others. Imagine sending a message to your younger self that changes a choice you made. That altered choice could erase the very future in which you sent the message. Some theories attempt to resolve this by suggesting that the past is immutable. You could visit it, but you couldn't change it. Anything you did there would already be part of history. Others propose that any change would simply branch off into a new timeline, leaving the original untouched. These ideas are intriguing, but they remain firmly in the realm of speculation. We have no experimental evidence that backward time travel is possible, and much that suggests it may be forever forbidden. Yet forward travel is different. That's the kind we've already observed and measured, and it requires no breaking of the universe's rules. It's not about jumping through magical portals. It's about shaping your path through spacetime so that your personal clock runs slower than the clocks around you. And this is where relativity reveals its quiet wonder. Time is not universal. There is no single cosmic clock ticking away in perfect unison for all observers. Instead, each person, each object, each particle experiences time at a rate determined by its motion and the gravity around it. This is why astronauts, high-speed particles, and even satellites live slightly different timelines from ours. The differences are small under everyday conditions, but they're always there, woven into the fabric of the universe. Imagine if we could push those conditions to extremes. A spacecraft traveling at 99.999% of the speed of light could turn a few years of onboard time into centuries of Earth time. Or a research station placed just outside the event horizon of a black hole could experience days, while the rest of the universe races ahead by decades. These are not fantasies. They are direct consequences of the equations we already trust. The challenge, of course, is engineering. Reaching such speeds or surviving near such intense gravity requires technology far beyond what we possess today. But the fact that the physics allows it means it's a problem of how, not if. This changes the way we think about our place in the cosmos. Time travel into the future is not some supernatural trick, it's a form of navigation. Just as a sailor chooses a route through the seas, a traveler can, in theory, choose a route through spacetime that carries them far ahead of those who stay behind. And in this light, the universe becomes a vast ocean of personal timelines, each flowing at its own pace. You are sailing one now, bound to Earth's steady gravity and speed. Others, out there among the stars, may be moving faster or slower, experiencing realities that unfold on entirely different scales. It's humbling to think that two people could meet, part ways, and reunite to find that for one, a short time has passed, while for the other an age has gone by. This is the bittersweet heart of forward time travel. It offers the wonder of seeing the far future, but at the cost of losing touch with the present you left. The world you return to will not be the one you remember. In a way, that truth is already familiar to us. Life itself is a one-way journey. We grow older, the world changes, and moments we once knew slip out of reach. Every step forward in time is also a step away from something we can't return to. And yet this is also what makes the future worth reaching for. It is unknown, and in that unknown lies possibility. Time travel in its real and measurable form is simply the extension of what we already do, moving into tomorrow and the day after that at the pace set by our chosen path. Perhaps someday, technology will give us the means to choose that pace freely. Until then, we travel together second by second into a future none of us has yet seen. And maybe that's enough for now. When we talk about time travel in everyday conversation, it's easy to think of it as something separate from normal life, an extraordinary event that happens only in science fiction. But the truth is, you are already a time traveler. Every moment you live is a step into the future. The seconds behind you are gone, the seconds ahead are yet to arrive, and you are always moving forward, carried by the steady flow of time. The difference between this ordinary travel and the extraordinary version lies in the size of the leap. Most of us move in sync with the people and world around us, but under the right conditions, high speed, strong gravity, your pace can change. You can live fewer moments while others live more, so that when you meet again, they have aged further than you have. This is not just theory, it's been measured. Astronauts on the International Space Station orbit Earth at over 17,000 miles per hour. Because of both their velocity and the weaker gravity at their altitude, their clocks tick slightly slower than those on the surface. The difference is tiny, measured in fractions of a second, but it's real. And in principle, that same effect could be magnified. A spacecraft moving close to the speed of light, or orbiting near a black hole, could let its crew leap centuries into the future in what feels like only a few years to them. The concept may seem abstract, but its reality comes down to something deeply personal. Time is not the same for everyone. It's shaped by your path through the universe. This makes time travel less like a jump and more like a journey, one where your route determines how far ahead you'll arrive. You can think of it as sailing a river whose currents run at different speeds in different channels. Choose the right current, and you'll reach the distant shore far sooner than others traveling alongside you. The key to this journey lies in two effects described by Einstein's relativity: time dilation from speed and time dilation from gravity. Both have the same outcome. Your personal clock ticks slower than someone else's, but the cause is different. In the case of speed, it's about your motion relative to another observer. The faster you go, the more your time stretches. At everyday speeds, this difference is negligible. At near-light speed, it becomes profound. In the case of gravity, it's about your position in a gravitational field. The stronger the field, the slower your time compared to someone farther away from it. That's why time on Earth's surface passes slightly slower than time in orbit. Combine the two effects, and you can amplify the leap. A ship moving quickly in a deep gravitational well would experience time at a much slower pace than the rest of the universe. But this brings us back to a hard truth. The universe gives no easy path. The energy required for such speeds is staggering, and surviving the environment near a massive object is a challenge we're far from overcoming. Still, knowing that the physics allows it changes our perspective. Time travel into the future is not magic, it's a natural feature of spacetime. We see it in the decay rates of particles, in the ticking of atomic clocks, in the lives of astronauts. The principle is already at work. The only limit is how far we can push it. And in thinking about this, another thought emerges. If time can flow differently for different observers, then somewhere in the universe, it must already be doing so in dramatic ways. Worlds orbiting massive stars, or circling black holes, may live on a slower clock than ours. Civilizations there might see our history unfold in fast motion, just as we might see theirs in slow motion. This also means that contact between such civilizations could be strange. A message sent to them might be answered years, or even centuries, later from our perspective, but only months later from theirs. Their entire sense of history and change would be different from ours. It's a reminder that the universe is not just vast in space, but vast in time. Every corner moves at its own rhythm. And in this great cosmic symphony, our little section plays at a tempo set by Earth's speed and gravity. When you realize this, the line between normal life and time travel begins to blur. You are already part of the same story, already on a path through spacetime. The only difference is how far ahead you can choose to go. And while the engineering may be beyond us for now, the concept is not beyond our understanding. The same equations that explain the bending of light around stars also explain the bending of time. The same mathematics that predicts the orbit of planets predicts the leap a traveler could make into the far future. It's humbling and perhaps a little comforting to know that the rules are consistent. The universe does not hide its laws from us. It invites us to discover them, piece by piece, test by test. So the next time you think about time travel, remember, it's not just a dream or a story. It's something you're already doing quietly, constantly. And one day, we may learn how to take that small, steady journey and turn it into a leap. Until then, the future is still waiting, and you're already on your way to meet it. When we imagine the far future, it's easy to picture it in vivid detail, cities that shine with strange architecture, skies lit by unfamiliar stars, and technologies we can barely dream of. Yet if someone were to actually travel there, the experience might be far more subtle than the stories suggest. To the traveler, the leap into the future wouldn't feel like a leap at all. Time wouldn't skip forward in bursts. It would simply flow at a slower pace. Days would come and go, conversations would unfold, and the seasons would pass as usual. The difference would only be apparent at the journey's end, when the world outside had aged far more than the traveler had. This is the quiet magic of time dilation. It doesn't disrupt your life in the moment. It changes your relationship with everyone and everything else. Imagine stepping aboard a vessel built for speed beyond anything humanity has yet achieved. The engines ignite, and soon you're gliding through space at a fraction below the speed of light. Inside, you feel no strangeness. Gravity keeps your footing steady, and life continues in its normal rhythm. But outside, Earth spins on, and for every year you live, decades might pass there. Upon returning, the world could be unrecognizable. Generations might have come and gone. The landscapes you once knew could be reshaped by nature and human hands alike. Even languages might sound strange to your ears. This is the beauty and the cost of traveling far into the future. It offers a view no one else could have, a first-hand glimpse of what's to come, but it also demands leaving behind what you knew. And yet, forward travel doesn't require a fictional machine. It's already built into the structure of spacetime. We've seen it in the extended lifetimes of high-speed particles, in the drift of clocks on satellites, and in the lives of astronauts who return to Earth younger, by the tiniest fraction, than those who stayed. What we lack is the capability to amplify the effect to human scales. The energy demands are immense. The faster you go, the more energy it takes, and the climb toward light speed grows steeper the closer you get. Gravity offers another approach. A massive object slows time for those near it, compared to observers farther away. But to make a meaningful leap into the future, you'd need to be close to something truly immense, like a neutron star or a black hole. Of course, these environments are among the most dangerous in the universe. The same gravitational forces that could slow your time could also rip your ship apart. Radiation, tidal stresses, and the sheer difficulty of reaching such places make them a challenge far beyond our current reach. Still, the physics is sound. If technology could solve the hazards, a traveler could wait in the grip of extreme gravity and return to find the universe much older than when they left. This possibility changes how we think about time itself. We tend to see it as a shared, universal experience, but relativity shows us that time is personal. Two people can live side by side and yet measure different amounts of time passing. It also changes how we think about history and destiny. The past may be fixed, but the future is flexible, at least in how we arrive at it. A journey could take you a week, a month, or a lifetime, depending on the path you choose through spacetime. Some scientists even wonder whether future exploration of the cosmos will require this kind of travel. The stars are unimaginably far apart, and even the nearest are light years away. To cross such distances, we may need to embrace journeys that involve not just moving through space, but also skipping forward in time. In that vision, the first travelers to other star systems might return to find Earth transformed beyond recognition, not because of what they found, but because of the time they missed. And while that idea might seem sad, it also carries a strange promise. For those willing to make the leap, the future would unfold all at once, like the turning of a page in a book. This makes time travel less about escaping the present and more about choosing when to arrive in the unfolding story of the universe. You wouldn't change what has happened. You'd simply choose the moment in which to step back into the world. And perhaps that's the real allure of it. The knowledge that, in principle, you could stand at the edge of today and walk into tomorrow. Not tomorrow as we know it, but tomorrow as it might be hundreds or thousands of years from now. Until that day comes, we all continue the same journey, second by second. But the physics that could turn that journey into a leap is already here, waiting for us to build the tools to use it. And when we do, the future won't just be something we imagine. It will be somewhere we can visit. When people first hear that time is not fixed, that it can stretch and compress depending on speed and gravity, it often feels like a trick of words, a technical detail that can't really matter much in the real world. But the truth is, it matters everywhere all the time. The flow of time is woven into the structure of the universe, and every object, every observer, moves along their own timeline. No two are perfectly identical. Even here on Earth, the difference exists. A clock on a mountain ticks a little faster than one at sea level. A GPS satellite's clock runs differently from yours, and without constant adjustment, the entire navigation system would drift into uselessness within minutes. The technology that helps us find our way relies on accounting for relativity's quiet influence. Once you see this, the idea of time travel into the future stops being abstract. It's not about stepping into a magical device. It's about understanding how to change your own rate of time compared to the world around you. And this brings us to one of the most intriguing aspects of physics. The same rules that allow a particle to live longer when moving at high speed also apply to you. The leap from microseconds to centuries is a matter of scale and engineering, not a change in the law itself. This symmetry gives us a kind of roadmap. If we want to travel far into the future, we know how. We must either move quickly enough or place ourselves deep enough in a strong gravitational field. The mathematics are clear, the predictions tested. What remains uncertain is whether we can ever build machines or find locations that allow such leaps on a human scale. The energy requirements for near-light-speed travel are immense, and the environments near black holes are among the most dangerous known to science. Still, the universe is vast, and history shows that what is impossible for one generation often becomes routine for another. It's possible that someday, humans, or the beings that succeed us, will learn to navigate time as skillfully as we now navigate the oceans and skies. If that happens, the future will hold an entirely new kind of exploration. Journeys won't just cross distances, they'll cross centuries. The first explorers to set out for distant stars might return to find the Earth of their memories gone, replaced by something wholly new. Such a reality would transform our understanding of history. The gap between departure and arrival would no longer be measured just in miles, but in years, or even ages. And this would change not just travel, but communication, culture, and identity. It's humbling to imagine what it would mean for families, friendships, or societies. How would you say goodbye to someone knowing that, from your perspective, you might never see them again, even if they only experienced a few years? In this way, time travel into the future is both a scientific possibility and an emotional challenge. It offers knowledge, discovery, and wonder, but also separation, loss, and change. The leap forward is not just a physical journey. It's a step into a world where the people and places you knew have been shaped by years you did not live. And yet, perhaps that is why the idea is so compelling. It's not only about science, it's about the human story. We have always been travelers, seeking what lies beyond the next horizon. Time travel simply moves that horizon into the years ahead instead of the miles away. And whether or not we ever achieve it on a grand scale, the truth is, we are all already doing it. Every breath, every heartbeat, every step carries us forward. The pace may be slow, but the journey never stops. One day, perhaps, we'll take that knowledge and turn it into something extraordinary. We'll build vessels that sail not only across space, but through the flow of time itself. And when that day comes, the question will no longer be whether we can travel to the future. It will be what we choose to do when we get there. Until then, we keep moving together into the unknown. And in that movement lies the quiet miracle that we've been traveling through time all along. The more deeply you explore the science of time, the more you realize that it is not an absolute, universal thing. It is a personal experience. This is one of Einstein's most astonishing gifts to our understanding of reality. The realization that time is tied to the observer. Your clock is yours alone, shaped by where you are and how you move. Someone else's clock, moving along a different path, will not match yours perfectly. It's a simple truth with profound consequences. If two people meet, then part ways and take different journeys, one remaining still, the other moving at high speed or traveling near a massive object, they will not return to find their clocks aligned. They will have lived different amounts of time. On Earth, the difference is small. But in the cosmos, where speeds and masses can be extreme, the gap can grow to unimaginable scales. A traveler who spends a few years near a black hole might return to find that centuries have passed elsewhere. This is not speculation. It's an extension of effects we already observe in laboratories and in orbit. Atomic clocks confirm it. High-speed particles confirm it. The precision of GPS technology depends on it. And so, when we talk about traveling into the future, we are not speaking of fantasy. We are speaking of using these same effects deliberately, scaling them up until the difference in time becomes dramatic. The challenge, of course, is practical. To create a large leap in time, you must either travel incredibly fast or dwell in an extraordinarily strong gravitational field. Both require resources and protections beyond our current capabilities. But imagining it allows us to think about the universe in a new way. Time becomes not a single line, but a web of countless strands, each stretching forward at its own pace. And within that web, you can choose which strand to follow. This choice changes how you might approach exploration. Instead of simply asking how far away something is, you might also ask how far ahead in time it sits. A journey to a distant star could also be a journey into the future. If this becomes part of humanity's reality, it will reshape not just travel, but culture. The meaning of departure and return will change. The first people to venture far into space at high speeds may return to Earth as visitors to a world that has moved on without them. There is a deep poignancy in this thought. The excitement of seeing the future is balanced by the loss of the present. What you gain in knowledge, You give up in shared time with those you left behind. Yet perhaps that is the nature of all exploration. Every journey changes the traveler, and every traveler returns to a place that has changed in their absence. Time travel simply magnifies this truth, and it offers something else, a perspective on our lives here and now. Knowing that time is not absolute makes us appreciate the moments we share in the same frame of reference. It reminds us that the days and hours we experience together are precious precisely because they cannot be rewound or repeated. This awareness also softens the idea of waiting for the future. In a way, we're already on our way there. Every tick of the clock brings us closer, and every path through spacetime leads us forward. Whether that path is ordinary or extraordinary depends on the choices we make and the technology we build. One day, the leap into the far future may be as real as boarding a ship or stepping into a station near a massive star. For now, it remains a thought experiment with roots in proven science. But even as a thought, it changes us. It stretches the boundaries of what we believe is possible. It reminds us that our personal timeline is not the only one, and that, in the vastness of the cosmos, countless others are unfolding right now, each at their own pace. And maybe, just maybe, one of those timelines will intersect with ours again, far ahead of where we are now. Time is one of those things we live within every moment, yet rarely stop to consider. We notice its passage in small ways, the changing of seasons, the lines deepening on a familiar face, the fading of memories. But we seldom think about its structure, its flexibility, or its connection to the very shape of the universe. For much of human history, we treated time as a constant. A second was a second for everyone, everywhere. The great clocks of the world were set in harmony, and the ticking was thought to be universal. But in the past century, science has shown us something very different. Time is not absolute. It can be stretched, it can be compressed, and it depends entirely on where you are and how you move. This discovery changes everything about how we think of the future. If time can run at different speeds for different observers, then the future is not a single shared moment waiting for all of us. It's a landscape, with different paths leading there at different rates. Einstein's theory of relativity gave us the tools to map this landscape. The faster you travel, the more your personal time slows relative to others. The closer you are to a strong source of gravity, the more it slows again. And these effects aren't just theories. They've been measured, over and over, in experiments here on Earth and in orbit. What we haven't yet done is magnify them to the point where the difference becomes life-changing. For now, astronauts gain only fractions of a second on their trips around the planet. But the same equations that predict these fractions also predict leaps of years, centuries, or more, if we can find a way to create the right conditions. Such conditions aren't easy to come by. Near-light speeds require staggering amounts of energy. Massive gravitational fields tend to be found in places that are hostile to human life, like the edge of a black hole or the core of a neutron star. And yet, it's not impossible to imagine a future where such challenges are overcome. Technology has always been about turning the unreachable into the routine. One day, perhaps, humanity will stand on the threshold of voyages that combine both distance and time, arriving in places that are not just far away, but far ahead. If that happens, the meaning of exploration will shift. A traveler returning from such a journey might find their homeworld transformed beyond recognition, not because of what they discovered, but because of what they missed. This is the double-edged nature of time travel into the future. It gives you a glimpse of what is to come, but it takes you out of the flow of the life you once knew. The people you left behind will have lived years or decades without you. The conversations you might have had, the moments you might have shared, will be gone. And yet, perhaps this is part of its power. To see the future is to witness the unfolding of a story you didn't write, a continuation of the human journey beyond your own time. It's also a reminder that, in a sense, we're all doing this already. Every day carries us forward and we can never go back. We are all travelers through time, moving at the pace set by our own place in the universe. The difference is that in our current lives, we travel in sync with those around us. We share the same days and nights, the same decades. Time travel in the relativistic sense simply allows us to change that pace, to drift into a slower current, so that when we meet again, the world has flowed much farther downstream. Whether or not we ever master this on a grand scale, the idea itself is valuable. It shows us that time is not a wall we move past, it's a terrain we move through. And like all terrains, it has many paths, some fast, some slow, some winding, some direct. To choose a different path is to choose a different future. And maybe that's the greatest lesson of all, that the future is not just something that happens to us. It's something we can navigate in ways both small and vast. When you think about time travel, it's tempting to focus on the extraordinary, the impossible machines, the sudden leaps across centuries. But in truth, the reality of time travel, as physics describes it, is quieter. It's not about sudden jumps, but about the steady, measurable shaping of your personal clock compared to the clocks of others. In this sense, the most fascinating thing about time travel is that we're already doing it. Every object in the universe moves through spacetime along a unique path, experiencing a slightly different flow of time. These differences are almost invisible in daily life, but they are there, and they can be made larger. Relativity tells us how. Move quickly enough or get close enough to a strong gravitational source, and the seconds on your clock will stretch compared to someone far away or standing still. It's not magic, and it's not a violation of the rules. It's the rules themselves. This means that forward time travel doesn't require breaking the universe's laws. It simply requires using them deliberately. The obstacle is not nature, it's technology. We can't yet reach the speeds or survive the environments that would make a human-scale leap possible. But the math is clear. If we could, it would work. And so the question becomes not, is it possible, but what would it mean? If someone could travel into the far future, they wouldn't vanish and reappear. They would live each moment in sequence, just more slowly than the rest of the world. From their perspective, the journey might take only months or years. From everyone else's, it might take centuries. The moment they returned, they'd find themselves in a changed world. New cities, new languages, new faces. The familiar would be gone, replaced by the unknown. This is the gift and the cost of such travel. It offers a glimpse of what's to come, but it separates you from the life you left behind. You gain knowledge of the future, but lose connection to the present. It's not hard to imagine how such a possibility could reshape human life. Exploration would no longer be limited to space, it would extend to time. Scientists, historians, and dreamers could witness events far beyond their natural lifespans. Cultures could plant ideas and see their effects play out over centuries. But it could also create distance, not just physical, but emotional, between those who leap ahead and those who stay. The rhythm of shared life depends on moving through time together. When that rhythm is broken, the bonds of family, friendship, and community would have to adapt. And yet, in a way, we already know what that feels like. Time separates us even now. We move away from places, we grow apart from people, and we find ourselves in futures we never fully expected. Time travel, in the relativistic sense, simply magnifies this truth. It also offers a perspective we often overlook. That time is not a single, universal march. It is a flexible, living thing, shaped by motion and gravity, by the choices we make and the paths we take. In this way, the dream of time travel is not so different from the life we already live. We are all travelers, moving through a landscape of moments, each one unique, each one unrecoverable. The only difference is speed. And maybe, just maybe, the real magic is not in leaping to the end of the story, but in understanding that we are part of it right now, that every second we live is a step into the future, and that the future we arrive in will depend on the path we choose today. In the end, the idea of time travel, at least as science describes it, isn't about breaking rules or rewriting history. It's about understanding the rules as they are and realizing they allow more than we once believed. Forward travel in time is built into the structure of the universe. It's not a loophole or an exception. It's a natural outcome of relativity, a feature of spacetime itself. Every day, we all drift toward the future together. The difference is that some paths could take us there faster, at least, faster from the perspective of those we leave behind. These paths are defined by speed and gravity, and we already see their effects in tiny ways all around us. Clocks in orbit tick differently than clocks on the ground. Particles in accelerators live longer than they would at rest. Even your height above sea level subtly changes the rate at which time flows for you. From these small truths, the larger truth follows. If we can magnify the effect, we can leap far ahead. Travel close to the speed of light or wait near a massive object, and your time slows compared to the rest of the universe. Return from that journey and you step into a future far beyond your departure date. It's a strange kind of travel. You don't skip the moments, you live them all. You just live fewer of them than those you left behind. This makes it different from the way time travel is often imagined. There's no sudden flash, no instant arrival, just the quiet passage of days and nights while the rest of the universe races on without you. And yet, there's something beautiful in that. It reminds us that time is not an unyielding wall. It's a river, with currents that can run at different speeds. If you find the right current, you can drift ahead while the shoreline changes in ways you can only see when you return. Of course, the practical challenges remain immense. The energy needed for near-light-speed travel is staggering. The dangers of approaching massive objects are beyond anything we've yet overcome. But history tells us that impossible is often just not yet. Perhaps one day humans, or whatever we become, will stand on the edge of such a journey. They'll step aboard a vessel, leave the familiar behind, and set out on a path that will bring them not just to another place, but to another time. And when they arrive, they'll find a world transformed. New faces, new voices, new ways of living. The past they left will be gone, but the future they've reached will be theirs to explore. Until then, we keep moving forward second by second at the pace set by our place in the cosmos. And in a quiet way, that's its own form of time travel. Because whether or not we ever leap centuries in a single trip, we are all already on the same journey into tomorrow, and the day after that, and the day after that. It may not be as dramatic as the stories, but it's no less real. The future is out there, waiting. And every moment we live is one step closer to meeting it. If you enjoyed this quiet exploration, I'd be so grateful if you gave it a gentle like, left a thought or reflection in the comments, and shared it with someone who might also find comfort in it. Your support helps these peaceful journeys reach more hearts and minds. And now, as our time together draws to a close, I want to thank you for being here, for listening, and for letting your curiosity wander alongside mine. Please take good care of yourself. Be kind to your mind, rest your body, and allow the world to soften around you. May your night be calm, your dreams be gentle, and your sleep be deep. Until we meet again, this is the Sleepy Narrator wishing you peace, warmth, and the quiet joy of knowing tomorrow will wait for you.